Somewhere inside Google's quantum AI division, a small team of researchers spent the first months of 2026 quietly doing something that, on paper, sounds almost mundane, refining a set of mathematical circuits. No press conference, no dramatic reveal, just a research paper published alongside a cryptographic proof describing exactly how much smaller and faster a quantum computer would need to be to break the encryption protecting nearly everything you do online. When cryptographers outside Google actually sat down and read what was in that paper, the reaction wasn't panic qubits required to crack RSA encryption, the mathematical lock securing your bank, your email, and most of the internet's secure traffic had dropped by a factor of 20 in less than a year. This is the story of what Google's quantum AI team actually found, why the security community is treating it as a genuine turning point rather than a routine research update, and what it actually does and doesn't mean for the world right now. Before we get into it, if you're new here, this channel covers technology and science the way people who actually work in these fields talk about them, without the exaggeration. If that sounds like your kind of channel, the subscribe button is right there, and it genuinely helps this content reach more people who want the real picture. Beat 1, the lock that holds the internet together. To understand why this matters, it helps to understand what RSA encryption actually is and why so much depends on it. RSA, named after its three creators, Ron Rivest, Adi Shamir, and Leonard Adleman, is one of the most widely used encryption systems on Earth. It secures online banking, email, digital certificates, and huge portions of the traffic that keeps the modern internet functioning securely. Its security rests on a single, deceptively simple mathematical fact. Multiplying two enormous prime numbers together is fast and easy, even for an ordinary computer. But taking that resulting product and working backward to figure out which two primes created it is, for a large enough number, practically impossible for any classical computer to do in a useful amount of time. Modern RSA keys are typically built from numbers 2048 bits long, meaning the number itself, written out, would run to more than 600 digits. No conventional computer on Earth, no matter how powerful, could factor a number that large before the sun burns out. That's where quantum computers enter the story. Back in 1994, mathematician Peter Shor discovered an algorithm that, if run on a sufficiently large and stable quantum computer, could factor exactly these kinds of enormous numbers efficiently, something no classical algorithm has ever come close to achieving. For decades, that discovery was treated as a fascinating but largely theoretical threat, because building a quantum computer big enough and stable enough to actually run Shor's algorithm against a real 2048-bit RSA key seemed to require millions of physical qubits, a scale of hardware that felt comfortably distant, decades away at best. That comfortable distance is exactly what's been shrinking fast over the past year. Beat 2. The first crack. The shift started in earnest in May 2025, when Google quantum AI researcher Craig Gidney published a paper showing that breaking a 2048-bit RSA key might require fewer than 1 million noisy physical qubits, running for less than a week, to succeed. That number sounds enormous in absolute terms, and it is. Current quantum computers today have nowhere near that many working qubits. But relative to what the field believed just a few years earlier, it represented roughly a 20-fold reduction from prior estimates made back in 2019. The improvement didn't come from some radical new type of quantum hardware. It came almost entirely from smarter algorithms, more efficient error correction, and cleverer circuit design squeezing dramatically more capability out of the same theoretical class of machine. In cryptography, there's an old grim axiom that practitioners repeat to each other. Attacks always get better, they never get worse. Gidney's paper was a fairly stark demonstration of that principle playing out in real time. Beat 3. The second crack, and why it mattered even more. If RSA were the whole story, this would already be a significant piece of news. But in March 2026, Google's team led by researchers Ryan Babish and Hartmut Nevin, and working alongside co-authors from Stanford and the Ethereum Foundation, turned their attention to a different related form of encryption called elliptic curve cryptography, or ECC. This is the mathematical system underpinning the security of Bitcoin, Ethereum, and most other major cryptocurrencies, along with a substantial share of the digital signatures used across the wider internet. Because elliptic curve keys are mathematically denser than RSA keys at an equivalent level of security, a smaller quantum computer can, in principle, threaten them. The new white paper, published March 30th and 31st, 2026, demonstrated that breaking 256-bit elliptic curve cryptography, the specific standard used to secure Bitcoin and Ethereum, could require somewhere between 1,200 and 1,450 logical qubits, translating to fewer than 500,000 physical qubits on a realistic superconducting architecture, completing the attack in somewhere around 18 to 23 minutes of actual runtime. The previous best published estimate from a 2023 paper had put the requirement at roughly 9 million physical qubits using a photonic architecture. Google's new numbers represented, once again, roughly a 20-fold reduction achieved in under 3 years. Some of the specific circuit designs in the paper needed 84% fewer logical qubits than earlier approaches, and a separate variant optimized for speed, rather than qubit count, cut the number of required computing operations by around 73%. Beat 4. How Google disclosed it without handing out the blueprint. Here's a detail that's genuinely unusual, and it's worth understanding, because it shaped how the rest of the research community responded. Google's team chose not to publish the actual quantum circuits behind their new estimates. Instead, they released what's called a zero-knowledge proof, a cryptographic technique that lets independent researchers verify a mathematical claim is true without the original researchers having to reveal exactly how they did it. In practical terms, Google proved they possessed working circuits capable of performing the underlying elliptic curve mathematics correctly across thousands of random test cases, without ever publishing the circuits themselves. The proof was generated using something called the SP1 zero-knowledge virtual machine, and it let outside cryptographers confirm the claims were mathematically sound without handing anyone, including any adversarial actor, an actual usable blueprint for building the attack. Google has said it engaged with the United States government while preparing this disclosure, and researchers in the field have started pointing to this approach. Proving a vulnerability is real without publishing the exploit as a potential model for how sensitive quantum vulnerability disclosures should be handled going forward, rather than a one-off decision specific to this paper. Beat 5. The part that surprised even the experts. It's worth pausing to note that this result caught seasoned cryptographers off guard, not just casual observers. David Zhao, a professor and chair of combinatorics and optimization at the University of Waterloo, who wasn't involved in the research, described the results as genuinely surprising. Researchers in the field had generally expected improvements to continue arriving gradually, incrementally, year over year. What they got instead was a repeated pattern of 20-fold jumps, arriving on a timeline of months rather than years, driven almost entirely by smarter mathematics rather than by any dramatic new quantum hardware breakthrough. That distinction matters enormously for how seriously to take the threat right now. Google's paper does not claim that a working, cryptographically relevant quantum computer currently exists. It does not claim that Bitcoin, Ethereum, or standard internet encryption is broken today. The largest quantum processors that actually exist right now, machines like IBM's Condor, top out around 1,100 to magnitude 600 physical qubits, several orders of magnitude, short of the roughly 500,000 physical qubits Google's own paper says would be needed to execute the attack. What the paper demonstrates isn't an active attack. It's a dramatically shortened engineering roadmap, a much clearer, much closer target for what a future adversary would actually need to build. Beat 6. What's already vulnerable and what isn't. It's worth being specific about what this threat actually applies to, because the risk isn't evenly distributed. Google's paper explicitly notes that most Bitcoin holdings, specifically those using older transaction address types, where the public key itself has never been exposed on the blockchain, remain protected from this particular style of attack, at least while they stay unspent, because the underlying public key needed to run the quantum algorithm against isn't actually visible yet. Funds and accounts where a public key has already been exposed, whether through an older address format, a reused address, or certain types of active smart contract, sit in a meaningfully more exposed position once a large enough quantum computer eventually exists. The same logic extends to internet encryption more broadly. Security researchers have been warning for years about something called harvest now, decrypt later, the strategy where an adversary captures and stores encrypted internet traffic today, traffic they currently cannot read, banking on the ability to decrypt it retroactively once sufficiently powerful quantum hardware eventually becomes available. Google's new estimates don't change whether that strategy works in principle. What they do is shrink the amount of future quantum hardware an adversary would eventually need to make that stored, harvested data readable, which is precisely why organizations holding long-lived sensitive data have been told to treat this as an accelerating, not a distant, planning problem. Beat 7. Google's own deadline. Perhaps the clearest signal of how seriously Google itself is treating this sits in a detail buried inside the same March 2026 announcement. Alongside the technical results, Google disclosed an internal deadline. The company intends to migrate all of its own infrastructure to post-quantum cryptography, meaning encryption specifically designed to resist quantum attacks, by 2029. That's not a distant symbolic target. It's a company that builds quantum hardware, develops the algorithms that attack current cryptography, and simultaneously runs a global technology infrastructure that depends on the very cryptographic systems its own research keeps proving are weaker than previously believed, setting a 3-year internal clock for its own migration away from that risk. Government agencies have been moving on a broadly similar timeline. The U.S. National Institute of Standards and Technology has laid out a deprecation schedule calling for quantum-vulnerable algorithms like RSA 2048 to be phased out after 2030 and formally disallowed after 2035. The National Security Agency's own Framework for National Security Systems requires new systems to be quantum safe by January 2027, considerably sooner than the broader civilian timeline. None of these deadlines exist because anyone believes a cryptographically relevant quantum computer is sitting in a lab somewhere today, ready to go. They exist because migrating an entire cryptographic standards is an enormous, slow, expensive undertaking in its own right, one that has to start years, arguably decades, before the actual threat fully materializes if it's going to be finished in time. Beat 8. It's not just Google. Google isn't operating in isolation here, and understanding the wider research landscape helps explain why the security community responded to these papers as a genuine inflection point rather than one company's marketing. Within days of Google's March 2026 elliptic curve paper, a separate research collaboration between Caltech, Berkeley, and a company called Oratomic published a preprint exploring the same underlying problem using an entirely different quantum hardware approach, one based on neutral atoms trapped and arranged individually using laser tweezers, rather than the superconducting circuits Google's own hardware relies on. Their estimates suggested that Shor's algorithm could potentially be implemented using as few as 10,000 to 20,000 atomic qubits, and that a system built around roughly 26,000 qubits could, in principle, break Bitcoin's specific elliptic curve encryption within a matter of days. That's a meaningfully different, and in some ways more aggressive, estimate than Google's own superconducting-based figures, and it illustrates an important point. This isn't a single research group's finding that the rest of the field can dismiss as an outlier. It's multiple independent teams using different hardware assumptions and converging on the same broad conclusion from different directions that the resources required to threaten modern cryptography are shrinking faster and along more paths than almost anyone expected even a year earlier. Researchers tracking the field have started describing 2025 and 2026 collectively as the period when 3 separate major papers rewrote the quantum threat timeline within roughly 12 months of each other, compressing estimates that had stood essentially unchallenged since 2019 and 2023. There's also a competitive, almost adversarial energy that's crept into this corner of research, worth noting because it suggests the pace isn't likely to slow down soon. Within 72 hours of one set of Google's published results, a separate quantum-adjacent startup working with crowdsourced computation and coordinated AI systems claimed to have matched or exceeded parts of Google's own optimization results, illustrating just how quickly outside teams are now able to build on, verify, and in some cases outpace the original published work once it's out in the open. Whether or not every one of these follow-on claims fully holds up under scrutiny, the underlying trend is consistent across nearly all of them. The qubit and gate counts required to threaten modern cryptography keep getting smaller from multiple independent directions at a pace that has genuinely surprised specialists who've spent their careers studying this specific problem. Beat 9. The quiet infrastructure. Already being built. While the public conversation around this story has largely focused on the headline, grabbing qubit numbers, a quieter, less visible response has been building in parallel across governments and industry for the past few years. And Google's 2026 papers landed directly on top of that existing groundwork, rather than starting it from scratch. NIST finalized its first set of standardized post-quantum cryptographic algorithms back in 2024, giving organizations concrete vetted replacement standards to migrate toward rather than leaving them to invent their own defenses. In the United States, the Quantum Computing Cybersecurity Preparedness Act now legally requires federal agencies to inventory which of their systems currently rely on quantum vulnerable cryptography, and to report their migration progress annually, turning what used to be a purely voluntary best practice into an enforced compliance requirement. A 2025 executive order, explicitly built on that same policy foundation, describing quantum safe migration as a continuing bipartisan federal priority rather than a partisan or optional initiative. Private industry has been moving in parallel. Google itself has been rolling out quantum safe HTTPS certificate support inside Chrome, meaning the browser millions of people use every day has already begun quietly supporting encryption standards, designed specifically to resist the kind of attack its own research keeps making more concrete. Major hardware manufacturers, including companies like Dell and HP, have started shipping quantum-resistant security features built directly into new devices, aimed at protecting sensitive data for years or decades into the future. well past the point, when today's encryption standards are expected to still be considered safe. None of this infrastructure is being built because a working attack exists right now. It's being built because migrating an entire global technology stack away from decades, old cryptographic assumptions takes years even under ideal conditions, and the organizations responsible for that migration have concluded, collectively and independently, that ideal conditions no longer include the luxury of waiting. Why this matters. Nothing about this story means your bank account, your email, or your cryptocurrency wallet is at risk of being drained tomorrow. The hardware gap between what exists today and what Google's own paper says would be needed remains enormous, roughly 1,000-fold in terms of physical qubits, and building stable, error-corrected quantum hardware at that scale remains one of the hardest open engineering problems in physics. What has genuinely changed is the shape of the timeline. A threat that felt comfortably theoretical, safely decades away, has been repeatedly, measurably compressed by smarter mathematics rather than by any single dramatic hardware leap, and the pattern of those compressions, 20-fold, then 20-fold again, arriving faster each time, is exactly the kind of trend line that turns planning documents into urgent ones. It's worth being honest about the limits of forecasting here too. Every one of these papers is, fundamentally, a theoretical estimate rather than a demonstrated attack. Building error-corrected qubits at the scale these papers describe, hundreds of thousands or millions of physical qubits working together reliably enough to run a multi-day computation without the whole system collapsing into noise, remains an unsolved engineering problem, and reasonable experts in the field still disagree about how many more years, or decades, that engineering challenge will actually take to solve. What almost nobody in the field disagrees with anymore is the direction of travel. Every major published estimate over the past 3 years has moved the same way: fewer qubits, fewer gates, shorter run times, and each new paper has arrived faster after the last one than experts predicted going in. This is, in a very real sense, a story about how the world quietly prepares for slow-motion emergency well before that emergency actually arrives. The cryptographic backbone of the internet was built assuming certain mathematical problems would stay impossibly hard forever. That assumption isn't failing today, but the margin protecting it, measured in qubits, in years, and now in the number of research papers required to meaningfully shrink that margin further, keeps getting smaller, and the people whose job it is to track that margin professionally are the ones telling you calmly and specifically that it's time to start moving. Closing. So no, Google's quantum AI team didn't stop the world, and nobody at Google or anywhere else in the field is claiming they broke the internet's encryption this year. What they actually did was publish, carefully and responsibly, exactly how much closer that possibility has become, prove it mathematically without handing anyone a working weapon, and set their own internal clock for getting ahead of a threat they helped make more concrete. The migration to quantum-safe cryptography isn't a future problem anymore. According to the people building the very tools that would eventually break the old locks, it's already underway. There's a version of this story that plays out over the next several years, largely invisibly to most people. Browsers that quietly start supporting new certificate types. Banks and payment processors gradually rotate their back-end systems onto post-quantum standards well before any customer notices a difference. Cryptocurrency protocols debate, sometimes contentiously, how and when to migrate wallets and signature schemes without disrupting a system worth trillions of dollars while it's still in active use. None of that will feel dramatic while it's happening, which is, in a sense, the entire point. The infrastructure being built right now exists specifically so that whenever a genuinely dangerous quantum computer does eventually arrive, the locks it's designed to pick will have already been quietly replaced. If deep dives like this into real, sourced technology news are what you come here for, subscribing helps this channel a lot. Drop your thoughts on the quantum encryption timeline in the comments. It genuinely shapes what we cover next. And sharing this with someone who still thinks quantum computing is decades away is the easiest way to support the channel.